Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. Tonight, you are drifting into the quiet mathematics of collapse, into the gentle way a star can fold inward under its own weight and become something the universe treats not as an object, but as a region of spacetime with its own rules, its own boundaries, its own gravity-shaped silence. This is a calm exploration, a slow, fluid, tranquil descent through ideas, not a lesson you must solve, not a story you must follow step by step, only a space to rest inside. As the concepts settle around you like soft particles drifting in a still field, you do not need to hold on to anything, not every detail, not every term, only the feeling that science, even in its most extreme predictions, can be gentle and deeply soothing. So let yourself settle, breathing slowly, listening lightly, as we begin with something simple and universal. A star is a balance, a long, steady conversation between two forces, pressure pushing outward, and gravity pulling inward, each keeping the other in check, each shaping the star into the sphere of light you know. Pressure comes from fusion, from atoms merging deep inside the core, from heat building, from energy expanding, from the constant, patient work of nuclear reactions that have been unfolding for millions, sometimes billions of years. Gravity comes from mass, from the star's own weight, from the curvature it creates in space-time, that gentle, persistent attraction that never stops pulling inward, never becomes tired, never releases its hold. For most of a star's life, these two forces rest in perfect equilibrium, a quiet standoff, a stable harmony, a balance so smooth that the star appears still, despite the ceaseless activity within. It is this balance that makes the idea of collapse so calm tonight, because collapse is not an explosion here, not a violent moment, but simply what happens when the outward pressure slowly fades, when fuel is used up, when the star can no longer push back hard enough, and gravity, softly, inevitably, begins to win. Imagine it this way, a delicate structure, held open by warm breath, slowly losing its warmth until the inward pull, the weight of itself, draws it closed. There is no rush, no sudden break, only the quiet shift in a balance that can no longer be sustained. And tonight, you are not tracking the history of stars or following a timeline of cosmic events. You are drifting through concepts, floating from one idea to the next, letting physics unfold like a soft night sky. So as you rest, imagine gravity as a kind of hunger, not aggressive, not consuming, but patient, steadily gathering matter toward the center, shaping everything with a gentle curvature, allowing stars to exist, and eventually guiding them to their transformation. This journey toward a black hole begins long before the name black hole has any meaning. It begins in the heart of the star itself, as the last reserves of nuclear fuel diminish, as pressure weakens, as atoms can no longer provide enough force to keep the star inflated. The star does not collapse all at once. Its outer layers may still shine, still radiate, still drift in their vast orbits, while deep within, the core begins to contract, slowly, quietly, under a gravity that has always been there, waiting. You may picture the core becoming denser, atoms pressed so close that their electrons are forced into new states, matter transforming under pressures that exceed imagination, density rising, temperatures increasing, as the core shrinks to a fraction of its former size. But all of this, in the calmness of tonight, is simply the story of balance giving way, of an object settling into the configuration that gravity prefers, the configuration that spacetime itself dictates. Nothing else needs to be decided here. You do not need to recall the exact pressures, the equations, the temperatures, only the idea that collapse is a natural response, a gravitational requirement, when outward pressure can no longer keep up. In this unfolding, What seems drastic from a distance feels gentle from within, because every step follows a smooth gradient of physics, a gradual deepening of curvature, a slow, inward settling. The star is not falling into chaos. It is falling into simplicity, into a state where only gravity's rules matter, where structure no longer resists, and where matter yields to the geometry around it. As the core contracts, space-time curves more strongly, and the inward pull becomes more focused, more dominant, more absolute, but still quiet, still smooth, still part of the universe's natural progression. You might imagine the star's interior like a landscape folding inward, valleys deepening, gradients steepening, until motion, no matter how light or fast, is guided toward the center, not through force, but through geometry. In this introduction, we will not yet cross the event horizon. We will not reach the point of no return, not yet. We are merely approaching the idea that such a boundary exists, a surface defined not by matter, but by the very shape of space-time. Before a black hole forms, before anything dramatic occurs, there is simply the soft, mathematical truth that gravity is stronger than pressure, that collapse becomes unavoidable, that the core contracts past the limits atoms can bear. And this is enough for now, enough to settle into the idea that stars, even the most massive and powerful ones, are held together by delicate balances, balances that can shift, that can fail, that can lead to beautiful, mysterious outcomes. Tonight, you are not witnessing destruction, you are witnessing transformation, the conversion of a radiant, complex object into one of the simplest structures in the universe, a region described only by mass, spin, and charge, with all other details removed, softened, smoothed into the background. It is the universe's way of reducing complexity, its way of letting gravity complete the work it has always been doing, drawing matter inward, tightening the curvature, allowing the star to become something new. So as you drift further, know that this journey is gentle, guided by stable equations, rooted in physics that unfold predictably, even in their extremes. You are resting in the calm logic of collapse, a logic that does not hurry, does not demand, does not disturb, but simply unfolds like a slow inhalation followed by an equally slow release. You are entering a space where time stretches, where forces balance and unbalance, where gravity reveals its quietest, deepest nature. You are entering the beginning of the birth of a black hole. And now, slowly, softly, we drift toward the first idea, the persistent, shaping pull that has guided stars since their first moments. Gravity's gentle hunger. Gravity has always been here, quiet, patient, a sculptor that works without hands, shaping stars with nothing more than the gentle curvature of space-time. And in this moment, as you lie still, you can drift into the idea of gravity not as a force that presses or pulls, but as a pattern, a bending of the paths that matter naturally follows, a soft guide that turns motion inward, toward the center of mass, toward the deepest part of the star's interior. When a star is young and warm and bright, gravity is balanced, held in check by the pressure of fusion, the outward push of energy created deep in the core, a push so steady, so sustained, that the star remains swollen against its own weight. You might imagine this balance like two hands pressed gently against each other, neither overpowering, neither yielding, each contributing to the stillness between them. Gravity pulls inward, pressure pushes outward, and the star rests in equilibrium. A quiet, delicate equilibrium, one that persists for millions, sometimes billions of years, but one that can never last forever. Tonight, you are drifting into the beginning of its ending, into the first subtle change in that balance, the almost imperceptible moment when pressure begins to weaken, so slowly, so gradually, that from far away the star appears unchanged, still glowing, still stable, still serene. But inside, deep within the core, the equations begin to shift. Fusion consumes its fuel, hydrogen turns into helium, helium into heavier elements, the temperature adjusts, the rate of reactions evolves, and the pressure begins to fail. Not all at once, not dramatically, but like a breath being exhaled just a little too long, until the inward pull gains the smallest advantage. At first, gravity only wins by the faintest margin. So small it would seem irrelevant, yet gravity is patient, and any imbalance, no matter how slight, is enough to begin a slow inward drift. The core contracts, matter settles more tightly, density increases, and as the core grows denser, gravity strengthens. because the closer matter becomes, the more intensely it curves spacetime around it. You can think of it as a feedback loop, but a gentle one, a loop where contraction deepens gravity and gravity deepens contraction, not in a runaway surge, but in a gradual, persistent, mathematically inevitable progression. And through all of this, the star is not yet collapsing in the way one might imagine. Nothing is falling freely. Nothing is spiraling violently. The outer layers still rest on the balance between their own pressure and gravity, still shining outward, still radiating. The collapse begins in the core alone, a quiet contraction hidden beneath layers of plasma, a transformation taking place behind the star's luminous surface. The physics of this moment are beautiful in their simplicity. Gravity never stops pulling inward. Pressure must constantly push outward to resist, and the moment that pressure fades, the collapse becomes unavoidable. In this sense, gravity is not an aggressor, not a force that overwhelms. It is a requirement, a curvature that spacetime imposes, a shape that mass must follow. And when pressure weakens, the shape changes. You might imagine spacetime bending just a little more deeply, its curves softening into a steeper gradient, so that the pathways matter once followed now tilt inward, guiding the core towards smaller and smaller sizes. This inward settling is not chaotic, it is not explosive, it is a star fulfilling gravity's preference, yielding to the geometry that its own mass creates. As the core contracts, the particles inside it are pressed closer, electrons forced into tighter orbits, atoms pushed into configurations they were never meant to maintain, matter becoming something new, under pressures that exceed anything found on planets, or in ordinary stars, or anywhere except in these extreme moments of stellar evolution. But you do not need to hold all the details. You do not need to track every atomic change. You can let the ideas drift over you, the way light drifts across the surface of a calm sea. Gravity continues its pull, steady, unaltered, unchanged by time, unchanged by the star's history, only responding to the amount of mass gathered at the core. In a sense, gravity is simple, brilliantly simple. And stars collapse because that simplicity does not bend to circumstance, because pressure can fail, but gravity cannot. For a while, the contraction is slow, held back by the structural strength of the atoms themselves, by the quantum mechanical resistance of electrons. But even these resistances have limits, limits set by physics, limits that define how dense matter can become before it must transition into something different. So the core shrinks, the density rises, and pressure seeks new ways to fight back, yet gravity remains slightly ahead, always slightly stronger. In this stage, the collapse is a whisper, a quiet narrowing, a soft deepening of gravitational curvature. If you picture the interior of the star, you might imagine each layer feeling the gradual shift, not in sudden motion, but in the changing balance beneath it, a support that subtly weakens, like a foundation settling just a little deeper into the ground. The outer regions still radiate heat, still glow, still appear stable from afar, but inside, the star's interior is beginning to fold into itself, and this folding is the first step in the birth of a black hole. The word collapse can feel dramatic, but here it is slow, quiet, guided by gradients of pressure and density, following the shape gravity creates, a shape that becomes steeper with each passing moment. As the core contracts, temperature rises, reactions accelerate, but these changes, though intense, still fail to overcome the inward pull, because fusion can only generate pressure where fuel remains, and as fuel dwindles, pressure fades. This fading is the true beginning, the quiet heart of collapse, and the reason black holes form from the most massive stars, because only massive stars reach densities and temperatures so extreme that even exotic forms of pressure eventually lose the battle. For now, we rest in this early stage. The stage where gravity's quiet hunger grows stronger, not in leaps, but in smooth, unbroken steps, each one bringing the core deeper into curvature, deeper into density, deeper into the space where the rules begin to shift. A star's collapse is not sudden, not catastrophic at first. It is the gradual release of an equilibrium that has been held for millions of years, an equilibrium that requires constant energy to sustain, and once that energy fades, gravity takes over. Silently, inevitably, with the calm confidence of a force that has always been patient and always will be. As you drift through these ideas, you can imagine the star not as a failing object, but as a structure relaxing into a new configuration, letting go of the equilibrium it once fought to maintain, and easing into a shape that gravity has been defining all along. This is the first hint of collapse, the beginning of the transformation, the soft release of pressure that marks the start of a long inward journey, the journey that will eventually lead to the birth of a black hole. And as the core deepens its curvature, as the gravitational gradient steepens, you drift with it, slowly, calmly, toward the next part of this inward descent. The moment when the balance fails completely and the core begins to fall, inward, with nothing left to hold it back. Gravity deepens its hold when pressure begins to fade. But even here, in this early stage of collapse, nothing is sudden, nothing breaks sharply. Everything unfolds in gradients, smooth, continuous, like the slow dimming of a lantern as its fuel runs low. The star is still vast, still radiant, still shining brightly into the cosmos. But beneath that luminous surface, the delicate conversation between pressure and gravity is shifting, becoming uneven, growing quieter on one side, and stronger on the other. Pressure, once fueled by abundant nuclear reactions, is losing its influence, not collapsing instantly, but weakening in a way that changes the balance at the core. This weakening is subtle, the kind of change that begins almost imperceptibly, a slight mismatch in forces, a gentle tipping of the scale, and gravity, steady and unyielding, begins to gain ground. If you imagine the core from within, you might picture the particles drifting closer, not rushing, not accelerating wildly, but settling, as if guided toward the center by the soft slope of a curved landscape. The deeper the matter settles, the denser the core becomes, and the denser it becomes, the more strongly gravity curves spacetime around it. This is gravity's quiet hunger, its persistent tendency to pull matter inward, to gather mass into smaller volumes, to deepen the curvature that spacetime forms around energy and mass. And in this stage, the first stage of collapse, the core behaves almost like a star within the star, a separate region where density increases, temperature rises, and the equilibrium is no longer sustainable. The concept of equilibrium is central here, because a star does not exist in spite of gravity. It exists because gravity keeps the core compressed enough for fusion to occur, and fusion creates the pressure that pushes outward, balancing the pull inward. A star is an engine, held in a delicate balance, and when that balance begins to tilt, the engine shifts into a different mode, a mode defined not by outward expansion, but by inward contraction. And yet, as the core shrinks, the outer layers are unaware. They continue to radiate, continue to glow, continue to exist in their long, stable equilibrium, while deep below, the architecture supporting them slowly changes. The density in the core increases rapidly on astronomical scales. But in the gentle retelling of tonight, this rapidity feels like a slow drift, a natural settling, a matter of gravity following its preference. You might imagine the core reaching a point where atoms are squeezed so tightly together, the electrons are forced into levels they would never naturally occupy, the pressure between particles starting to depend not on temperature alone, but on quantum mechanical principles. The resistance of electrons to being compressed into the same state. This new form of pressure, electron degeneracy pressure, arises from fundamental physics, from the Pauli exclusion principle, from the rule that two electrons cannot occupy the same quantum state, and for a moment, it halts the collapse. But this moment, though important, is temporary in massive stars, for electron degeneracy pressure has a limit, a maximum value it can reach. A boundary enforced by the physics of fermions and gravity, with its relentless inward pull, will eventually exceed this pressure, if the star's mass is great enough. Before that boundary is crossed, before the core collapses beyond electron support, the core enters a transitional state, a dense configuration where matter is compressed to extremes, and the balance between gravity and pressure becomes more delicate than ever. This balance, this fragile equilibrium, can feel like a tightrope, a narrow line where forces are nearly equal. Yet any subtle shift, any tiny change in density or temperature, can determine the future of the star. And gradually, quietly, gravity continues its inward encouragement, pressing the core to smaller and smaller states, until the density is such that electrons and protons begin to merge, forming neutrons, releasing neutrinos that escape into the surrounding layers, carrying energy outward in silent streams. But even this transformation, the shift from ordinary matter into neutron-rich matter, is only the next signal of collapse, not the collapse itself. Not the moment of free fall, only the deepening of gravity's influence. At this point, gravity is not simply stronger, it is more focused, more concentrated, curving spacetime ever more steeply, so that the interior becomes a region where each step inward leads to an even deeper gradient. This steepening is a quiet thing, invisible, silent, a change in geometry rather than a change in activity, a reshaping of the pathways that matter and light can take. The core is now a dense sphere, supported temporarily by neutron degeneracy pressure, another quantum mechanical resistance, more powerful than the electron pressure that came before, yet still governed by limits set by the mass of the star, limits that gravity continues to approach. The entire time, gravity has remained unchanged, constant, the same curvature that shaped the star at its birth. But now, as density rises, that curvature becomes more intense, more pronounced, more demanding. The star is being asked a simple question by gravity. Can pressure still hold you up? Can it still balance what mass demands? Can it still provide the outward force that defines your equilibrium? And as the core becomes heavier, as more layers collapse inward and add their mass, the answer begins to shift, slowly, inevitably, toward no. The collapse is not violent yet, not explosive. The outer layers remain suspended by their own pressure, their own heat, their own structure, while the inner layers continue to contract. A star does not collapse as one piece, but layer by layer, with each region responding to the forces acting upon it, following the rules dictated by density, temperature, pressure, and curvature. If you imagine the core as a series of shells, each one holds for a time, each one resists collapse for a moment until gravity's demand becomes too strong and that shell yields, adding its mass to the inner region, deepening the gravitational well even further. This is gravity's gentle persistence, its steady shaping, its quiet hunger. Not a hunger that devours, but one that gathers, one that draws matter inward, encouraging it into configurations that spacetime naturally prefers. Pressure weakens, gravity takes the lead, and the star begins its gradual transition toward the catastrophic threshold. This threshold, where electron degeneracy fails, and neutron degeneracy must take its place, marks the moment when collapse becomes more than a quiet contraction. It becomes acceleration, a response to gravity that pressure can no longer slow. But tonight, we are not yet at that moment, not yet at the point where the core plunges inward, not yet at the boundary where the collapse becomes unstoppable. We are still in the soft, slow dawn of collapse, the phase where the star is learning that its balance has faded, where gravity is beginning to reshape the interior, bending pathways, deepening curvature, drawing matter inward with steady inevitability. The star is still glowing, still shining to distant observers, still holding its form, but inside its destiny has shifted, its equilibrium has been lost, and gravity, patient, persistent gravity, has begun its work. This is the gentle beginning of collapse, the quiet overture to the birth of a black hole. And as the density rises, as the curvature deepens, as pressure slowly surrenders, you drift with it into the next stage, the moment when the core can no longer resist and begins its fall inward toward a state that spacetime has prepared. And gravity demands. Gravity has now shaped the core into a state where balance is no longer possible. And with every moment, every slight increase in density, the star moves closer to the threshold where collapse becomes unavoidable. You have drifted through the gentle deepening of curvature, through the slow weakening of pressure, through the quiet surrender of equilibrium, and the ideas of Section 1 have all settled, softly, into place. So now, the inward journey continues, deeper, quieter, into the moment where the core can no longer hold itself up and begins to fall. This is where the second stage unfolds, the stage where matter becomes too dense for atoms to maintain their structure, and the collapse accelerates into realms where even light, in the language of geometry, cannot escape the pull. The core, already dense beyond anything familiar, enters a regime where atoms themselves fail, not through destruction, but through compression so extreme that the boundaries between particles blur and new forms of matter arise. Imagine the atoms squeezed so tightly together, their electrons pushed inward, their orbitals collapsing under pressure, until electrons are driven into protons, creating neutrons, and releasing neutrinos that surge outward in silent, almost ghost-like streams. This transformation is known as neutronization, and it marks the beginning of the core's shift into something fundamentally different. A state where matter is no longer organized as atoms, but as a dense sea of neutrons packed so tightly that their quantum mechanical resistance becomes the dominant form of pressure. Neutron degeneracy pressure, one of the strongest known resistances to compression, rises up to challenge gravity, a final stand, a last possible barrier between the core and absolute collapse. For a short time, this new pressure halts the contraction or slows it, holding the core in a precarious balance. A balance governed by the limits of quantum mechanics, by the rules that fermions cannot occupy the same quantum state. But gravity, in a star massive enough to form a black hole, has gathered too much mass, curved spacetime too deeply, and the question becomes not whether gravity will exceed this neutron pressure, but when. There is a limit, a precise boundary encoded in the physics of neutron stars, called the Tolman-Oppenheimer-Volkoff limit, a mathematical threshold that describes the maximum mass a neutron-supported core can withstand, and beyond which even neutron pressure fails. This limit is not an approximation, not an estimate, but a fundamental boundary set by general relativity, quantum mechanics, and nuclear physics working together, and once the core exceeds it, collapse becomes irreversible. In massive stars, the core almost always exceeds this threshold, because the layers above, now falling inward under their own gravity, add mass to the collapsing interior, deepening the curvature, steepening the gradient, pushing the core beyond what neutron degeneracy can resist. And when this threshold is crossed, the collapse changes character. No longer a slow drift, no longer a quiet contraction, but a descent so steep, so extreme, that space-time itself participates. The core begins to fall inward, not because it is pushed, but because the geometry it inhabits leaves no other path. Every possible trajectory slopes downward, steeper and steeper toward the center. This is what physicists mean when they say the core falls faster than light can escape. Not that matter outruns light, but that the inward slope of spacetime becomes so deep, so curved, that all directions lead inward, even the directions light would normally take to move away. Light is not trapped yet, not fully, but the curvature is increasing so rapidly, so intensely, that outward motion becomes harder and harder until there comes a moment, a threshold, where outward paths completely disappear. But before that threshold arrives, there is the collapse itself, the core shrinking dramatically, density doubling and doubling again, in timescales that would feel instant if you were watching. But in this retelling are smoothed into gentle, continuous shifts. Imagine the core shrinking from hundreds of kilometers to tens to just a few. The same mass compressed into an unimaginably small volume. Each decrease in radius amplifying gravity, each step inward steepening the curvature, each moment bringing the core closer to the place where spacetime will no longer allow escape. This is where collapse becomes self-reinforcing, where gravity amplifies itself, where spacetime curves more strongly because mass moves inward, and mass moves inward because spacetime curves more strongly. The interior becomes a runaway gradient, a deepening well, a structure where the steepness increases with every fraction of a second, until the collapse accelerates toward a state that classical physics can barely describe. As the core implodes, the neutrons themselves begin to fail, their quantum pressure insufficient to stop the inward plunge, their structure distorted by gravity so intense that no known force can resist. And here, in this brief and extreme moment, the core transitions into freefall collapse. A collapse where spacetime around it stretches and curves so drastically that even light, the fastest signal possible, cannot maintain an outward trajectory. This is the entrance into the next stage, but before the event horizon forms, before the point of no return emerges, the collapse itself must be understood. You can imagine the interior as a region where every possible direction, every possible path a particle might take is tilted inward, not by force, but by the curvature of spacetime itself. General relativity describes gravity not as a pull, but as geometry, and in these final moments before the horizon forms, geometry becomes destiny. The collapse continues, density rising, curvature intensifying, until the core reaches the critical condition where no outward paths remain, where the speed required to escape exceeds the speed of light, not because matter tries to outrun light, but because spacetime no longer provides an outward route. This is the deeper meaning of faster than light, not motion, but geometry, a description of how the collapse reshapes the fabric of spacetime, closing off escape routes, folding all trajectories inward toward the forming singularity. The feeling of this stage, if one could feel it, would not be violent, but inevitable, a slipping, a surrendering to curvature, a soft, inexorable inward drift. Light bends, time stretches. Space contracts, all according to the equations that describe this collapse. The core continues its descent, falling into a region where density becomes so extreme, so compact, that no known form of matter can resist. And in this final arc of collapse, the boundary of no return, the event horizon, begins to emerge. But for now, you are resting in the deepening collapse, in the calm analysis of a core becoming too dense to resist gravity, in the quiet mathematics that govern its fall, in the soft, steady creation of a black hole's heart. You are drifting with it, deeper, into curvature, into density, toward the moment when a new structure appears in the universe, a boundary defined not by matter, but by spacetime itself, the horizon that forms quietly as the core continues to fall inward. The core is now in freefall, not the violent freefall of a collapsing building, but the smooth, irresistible descent of matter sliding along the steepest curve spacetime can form. There is no longer any meaningful resistance, no pressure strong enough to slow the inward motion, no quantum rule capable of holding the structure together. The core has reached the point where gravity's demand exceeds every counterforce nature can provide, and so the collapse deepens, accelerating as density rises because the smaller the core becomes, the more concentrated its mass, and the more intensely it curves the fabric around it. Imagine the collapse as a narrowing funnel, each moment drawing matter to a smaller region, and each reduction in size making the funnel steeper, its walls sharper, its depth greater. The collapse proceeds according to general relativity, not as matter falling through space, but as matter following the shortest paths in a geometry reshaping itself with every passing instant. The curvature increases, light bends inward more strongly, and space-time stretches so dramatically that outward motion becomes less and less possible. This is where the language of faster than light truly becomes meaningful, because the inward pull is not a speed, not a force applied to matter, but a geometric property, a reshaping of the grid lines that define motion. Light, the ultimate speed limit, still travels at its constant pace, but the paths that once allowed escape, the outward routes, have been tilted inward by the collapse itself. If you imagine standing at some point inside the core, you would find that no matter which direction you attempted to move, no matter how you oriented yourself, your future trajectory would curve downward, toward the center, guided not by choice, but by geometry. This is the beginning of trapped surfaces, regions where all possible future paths are directed inward, even for light. But trapped surfaces do not appear all at once. They emerge gradually, as the collapse intensifies, as curvature grows, as gravity's influence becomes absolute. The core shrinks from tens of kilometers to a few, and then to fractions, each reduction amplifying the inward pull, each moment pushing the region closer to becoming a black hole. The temperature in the collapsing interior rises to unimaginable values, not because heat is being generated in the traditional sense, but because kinetic energy increases as matter accelerates inward, and because the compression is so extreme, so absolute, that atoms, nuclei, and even fundamental particles find themselves at densities where their usual behaviors dissolve. Yet for all the intensity of these numbers, for all the extreme physics taking place, the collapse itself remains smooth, coherent, governed by predictable equations. There is a strange calmness in the mathematics of this moment, a clarity in the way general relativity describes the paths matter must follow, a quiet unfolding of inevitability. Neutrinos, escaped earlier during neutronization, stream outward into the star's outer layers, but their influence on the collapse is minimal. The core's interior is too deep, too dense, for these particles to reverse the course of events. The collapse continues, accelerating as space-time curves more sharply, and the gravitational potential deepens beyond what any form of matter can resist. Neutron pressure, once the final source of structural support, has been overwhelmed, And now the core is in a regime of physics where classical descriptions struggle, where quantum field theory and general relativity approach their limits, where our current understanding begins to thin, like a fabric stretched to transparency. The core's radius shrinks below the Schwarzschild radius, even before the event horizon fully forms, a subtlety often missed in simple explanations. Because the horizon is not a physical shell, not a membrane, but a surface defined by the geometry of spacetime. As the core collapses inward, the horizon forms around it, not by expanding outward, but by emerging at the location where outward paths vanish, where the speed required to escape becomes infinite, where light, even with its constant speed, cannot move outward because spacetime curves inward faster than it can compensate. This is one of the quietest, most elegant predictions of general relativity, that a horizon can form in the vacuum surrounding the collapsing core, before any specific piece of matter reaches it, as if spacetime anticipates the collapse, reshaping itself according to the mass that is about to arrive. Inside the core, pressure is now irrelevant. Support is impossible, resistance meaningless. Every particle continues its descent, every path slopes inward. The collapse becomes what physicists call geodesic, a motion defined by the straightest possible lines in a curved geometry, the natural fall dictated by spacetime itself. The interior becomes a place where time and space begin to interchange their roles, not metaphorically, but mathematically. The inward direction becomes as inescapable as the forward flow of time, and time stretches, lengthens, warps. To an external observer, watching from far away, the collapse appears to slow. Light from the infalling matter becomes redshifted, dimmed, time dilated, until the collapsing core seems frozen at the edge of the horizon. But this is an illusion, a perspective effect, a consequence of how spacetime reshapes the paths light must follow. Inside, the collapse continues at full speed, unaware of how it appears to distant observers, unaware of the infinite redshift that cloaks its motion, unaware of the distortion of time outside. For the infalling matter, the collapse proceeds normally, smoothly, inward, toward a state of increasing density, increasing curvature, increasing inevitability. The core becomes smaller, more compact, until its size is dwarfed by the Schwarzschild radius, lost inside the region where outward motion is impossible. And now the geometry becomes profound, because within the horizon, the radial direction behaves like time. The inward path is no longer optional, no longer a choice, but a requirement, as unavoidable as tomorrow following today. The collapse enters a regime where the equations of general relativity can still be written, still be solved, still describe motion, but where the densities and curvatures approach values that challenge our understanding, that drive physics into the realm of singularity. The matter inside cannot stop, cannot stabilize, cannot hover. It continues inward because spacetime itself guides it, forces it, defines its path. The feeling of this stage, if one could feel it, would be one of slipping deeper into narrowness, deeper into curvature, deeper into a region where all future moments point inward, as if drawn toward a single destination. As the collapse proceeds, the singularity forms, not yet explored in this narrative, but already taking shape as the endpoint of every inward trajectory, the place where density becomes infinite in classical physics, and where our equations, so powerful in ordinary conditions, grow silent. But before we reach that place, before we drift into the mystery at the center, there is one more threshold to understand: the emergence of the event horizon, the quiet boundary of no return, the surface that defines a black hole not by material substance, but by the geometry of spacetime. And so, as the core continues to collapse inward, as spacetime steepens into an almost vertical slope, you drift with it toward the calm, silent formation of the horizon, the smooth mathematical surface that marks the next stage of the birth of a black hole. The core has now passed the point where any form of matter can resist collapse, and the spacetime around it deepens into a geometry where inward motion becomes the only possible future, a quiet inevitability written into the curvature itself. The ideas of Section 2 are nearly complete, but a few final pieces drift gently into place, pieces that explain how spacetime curves so strongly, so profoundly, that even the concept of outside begins to lose meaning. The collapse accelerates, but acceleration here is not a violent lurch. It is the smoothing of motion, the disappearance of resistance, the transition from a complex structure into something simpler, more unified, more dictated by gravity alone. As the core continues inward, its mass becomes packed into an ever-shrinking region, and the curvature outside that region grows steeper, the inward slope becoming so extreme that the very shape of the future tilts toward the center. Light, which always travels at the same speed, finds itself directed inward, not because it slows, but because space-time around it bends, folds, reshapes its available paths. Imagine light as a traveler, seeking routes through a landscape whose hills and valleys are defined by mass, pressure, and density. In ordinary environments, there are paths that lead outward, paths that climb away from a gravitational well, paths that allow escape. But as the collapsing core approaches its critical state, these outward paths begin to narrow, tilt, fade, until every direction slopes downward toward the forming singularity, the future that gravity has chosen. This is what physicists call a trapped surface, a region where all future-directed paths, even those taken by light, lead inward. Trapped surfaces are not metaphors, they are mathematical structures, solutions to Einstein's field equations. Describing regions where the expansion of light rays is always negative, meaning they converge, they fall inward, they cannot expand outward into space. Once trapped surfaces form, the collapse becomes unstoppable, because even the fastest carrier of information, light itself, is confined to inward motion. And yet the outer world sees something entirely different, a different portrait filtered through the distortions of time. For a distant observer, the collapse seems to slow. Time appears to stretch around the falling matter. Signals become redder, fainter, dimmer, until they fade into darkness. This is gravitational time dilation, the slowing of time in stronger gravitational fields, a prediction of general relativity that becomes dramatic near the critical radius of collapse. The matter seems to hover just above the horizon, frozen in time, never quite crossing, never quite lost. But this is only appearance, only the external view, a consequence of how light struggles to climb out of deep curvature. Inside, the collapse does not slow, the matter continues to fall, unaware that its signals are stretched into invisibility, unaware that the outside universe perceives it as paused in place. The collapse completes itself in a smooth, unbroken sequence, guided not by force, but by geometry. The core plunges inward, past the radius where escape is impossible, past the boundary where time and space begin to exchange roles, past the place where outward motion is no longer defined. This is the true meaning of faster than light can escape, not the violation of a speed limit, but the reshaping of the very structure that determines which directions lead outward and which lead inward. When the collapse reaches this stage, the event horizon forms, the boundary that marks the newest black hole in the universe. But before the horizon fully settles, the collapse continues within the shrinking interior, the matter still falling, still compressing, still guided toward the singularity, the central point where classical physics ceases to function. Inside the horizon, the radial direction becomes a kind of future, a direction that all particles must follow, not by force, but by the geometry of spacetime. And outside, to the distant universe, the newly formed horizon appears still, silent, perfectly dark, a surface from which no light emerges, because the paths needed for escape simply do not exist. The final idea of this section, the last thread in the picture of the collapsing core, is the way spacetime itself becomes dynamic during collapse, not in the sense of motion, but in the sense of changing curvature, shifting geometry, reconfiguring the very structure of distance and duration. As the core shrinks, the spacetime around it adjusts, reshaping to reflect the deepening gravitational well, a well so steep, so extreme, that distances distort, clocks slow, and even the order in which events can occur becomes constrained. At the moment the horizon forms, the geometry reaches a threshold, a smooth, continuous, mathematical transition. From the outside, it appears as the sudden creation of a surface where outward paths end, but from the inside, it is simply the next consequence of gravity's unbroken logic, the next step in a collapse that began when pressure first weakened, long before neutrons formed, long before trapped surfaces appeared. And thus the ideas of Section 2 are complete. The transformation from atomic matter into neutron matter, the failure of neutron pressure, the TOV limit, the onset of trapped surfaces, the curvature increasing to a point where outward motion becomes impossible, and the collapse proceeding in a way that is described not by forces, but by the deep geometry of spacetime. Now, with these concepts resting quietly in place, we drift into the next stage, the stage where the event horizon itself forms, where the boundary of no return emerges as a calm, smooth, geometric feature, the most elegant line the universe can draw. The ideas gather, settle, and lead gently into Section 3, the quiet boundary, where escape becomes impossible, and spacetime folds inward toward the heart of the black hole. The collapse has now reached a moment where the nature of spacetime itself changes, quietly, smoothly, with a precision only gravity can create. All the ideas of Section 2 have settled into place, and the inward journey now carries you into the emergence of one of physics' most mysterious structures, a boundary defined not by matter, but by geometry. The event horizon. It forms not with a flash, not with a break, but with the softest shift in the curvature of spacetime. A moment when the outward routes that once allowed light to escape, fade, narrow, and then disappear entirely. Imagine this threshold not as a wall, not as a surface you could touch, but as a change in the shape of possibility, a moment where outward motion no longer exists as an option, where every path leads inward, not through force, but through the structure of spacetime itself. The event horizon is the surface where escape velocity equals the speed of light. But in this calm retelling, it is more illuminating to describe it as the place where the geometry becomes so steep, so inward curving, that light, despite moving at its absolute speed, cannot find a direction that leads away. It is often imagined as a sphere, dark, hollow, but its reality is more subtle. It is a smooth, perfectly symmetrical surface, defined only by spacetime curvature, by the mass inside, by the equations that describe how gravity shapes the future of every particle, every photon, every ripple of the fields that fill the universe. Inside the collapsing star, matter continues to fall, continues to compress, continues to descend inward toward even more extreme curvature, but outside, at a certain radius, the horizon emerges, not as matter crossing a boundary, but as spacetime responding to the unavoidable collapse, anticipating it, reshaping itself in perfect harmony with the core's descent. If you imagine space as a vast fluid, the horizon is like the point where a whirlpool becomes so deep that all streams, all flows, all directions lead inward toward the center. From the outside, nothing special appears to happen at this boundary. A particle crossing it would feel no jolt, no resistance, no rupture, because the horizon is not physical, not material, not a barrier. It is simply the location where paths turn inward, where the geometry demands a one-way direction, as naturally, as effortlessly, as time itself flows forward. This is why crossing the horizon feels like nothing at all, because nothing is resisting you, nothing is blocking you. Space is simply shaped so that forward motion, your future, lies deeper toward the center. To understand the event horizon, you can imagine light emitted in all directions from a point just outside it. Some rays escape, some are pulled inward, some curve and loop around, but outward paths still exist. Move a little closer, and fewer routes point away. Light becomes more confined, its escape more tenuous, each outward path bending inward slightly, as if gravity is carving deeper grooves into space-time. Then, at the horizon, every outward ray is balanced on the very edge of possibility, all pushed to their limit, all traveling along surfaces that neither gain distance nor fall. And any closer, even by the smallest fraction, light finds that every direction leads inward, every path curves toward the center, every future is guided into the black hole. This is the meaning of a trapped surface, a region where the outward expansion of light rays becomes negative, where all photons converge, no matter how they are emitted. From that moment on, the horizon exists perfectly, smoothly, as a surface beyond which nothing can communicate outward. To a distant observer, matter collapsing toward this boundary appears to slow, time stretching to infinity, signals redshifted until they fade into darkness, as if the falling star is suspended in time at the horizon's edge. But this is only the exterior perspective, a result of how light struggles to climb out of extreme curvature. From the perspective of the infalling matter, the collapse continues without interruption. The horizon is crossed smoothly, with no physical sign, no signal, no boundary that can be touched. It is one of the most profound predictions of general relativity, that the boundary marking the birth of a black hole is invisible, undetectable by the matter that passes through it, a purely geometric threshold. And yet, it is this threshold that defines everything. It marks the separation between the region where escape is possible and the region where all future paths lead inward. The horizon is the most important surface in the universe, not because of what happens there, but because of what becomes impossible beyond it. This impossibility is not dramatic, not explosive. It is the quiet disappearance of outward futures, a calm folding of spacetime into a simpler structure, a shrinkage of possibilities into a single direction. From here, time dilation grows stronger, curvature deepens, light bends with increasing intensity, and the fate of anything inside the horizon becomes inseparable from the geometry itself. The stars' remaining outer layers may still fall inward, still descend through the horizon, still contribute their mass to the growing black hole, but the horizon remains steady, calm, spherical, defined by the total mass gathered inside. As the collapse proceeds, the horizon may grow, but always smoothly, always continuously, responding to the infalling matter as if it were simply adjusting the curvature of space and time. There is a poetic subtlety in the way the horizon forms before the collapsing core reaches it. A statement from general relativity that the structure of the outside world reacts to the future collapse, anticipates it, reshapes itself in perfect alignment with the mass that it knows will arrive. To understand this gently, you can imagine spacetime as a fabric that begins to sag, deepen, curve inward, even before the weight fully presses down, because the geometry is determined not by the position of matter alone, but by its influence, its future motion, its unavoidable path. Inside the horizon, the collapse continues, guiding matter toward a place where our current equations will falter, toward the region where the singularity will form, hidden entirely from the outside universe. Outside the horizon, nothing appears different. Space continues, time flows, the universe carries on, but an invisible boundary now exists, the smooth, dark surface that marks the presence of a newborn black hole. This boundary is silent, perfectly calm, a mathematical horizon, not a wall, not a hole in space, but a region where escape becomes impossible, and where every path into the future leads inward. The event horizon now rests in place, quiet, unmoving, a smooth boundary shaped entirely by geometry, yet its presence transforms the meaning of inside and outside, future and past, escape and inevitability. To drift deeper into this idea, you can imagine the horizon not as a surface the star falls into, but as a surface that forms around the collapse, as spacetime reacts to the concentration of mass, curling its structure into one of the simplest shapes general relativity allows. A perfect sphere, defined not by matter, but by the curvature that mass creates. And because the horizon is not a material boundary, nothing announces its crossing. There is no sensation, no signal, no change in local physics. Everything feels normal until one tries to look outward and finds that the future, all directions of time and motion, lead inward instead. Inside the horizon, the inward direction becomes as compulsory as the next second of time, a geometric rule, a deep requirement that nothing can break. This is why the horizon is so peaceful, so gentle, because it is not a place of tearing or breaking, but a place where choices simply narrow, where the future becomes simple, unified, directed toward the singularity at the center. Outside the horizon, time and space behave in familiar ways. Directions retain meaning. Distances can be traveled. Objects can orbit. Light can move outward freely. But as you approach the horizon from outside, curvature grows steadily, space stretches, time slows, frequencies redshift, until motion begins to mirror the calm inevitability felt inside. This gradual approach is part of the horizon's nature. It is not sudden, not abrupt, but a seamless continuation of curvature deepening, a smooth transition from normal geometry to geometry that guides everything inward. One of the most fascinating predictions of general relativity emerges here, that the horizon forms first, before the collapsing matter reaches the location defined by the Schwarzschild radius. This means the horizon appears in the empty space outside the star, as if space-time is preparing a boundary, anticipating the collapse, because the equations describe not just the current state of matter, but the inevitable curvature produced by where the mass is going. It is a deeply counterintuitive idea that a horizon can exist before the matter that will be trapped inside it arrives. But this is the structure of gravity and general relativity, a structure that responds to mass and momentum not as isolated quantities, but as a complete, continuous field. Once the horizon forms, any additional matter falling inward only adjusts its size, never its nature, because the horizon is defined by mass as a whole, not by individual particles crossing it, and so the black hole becomes a stable, self-contained region of spacetime. Even now, the star's outer layers may not yet have reached the horizon, their collapse still unfolding, still guided downward, still following the path's curvature dictates. As they fall, light they emit becomes trapped, its wavelength stretched, its brightness diminished, its signals slowed by the gravitational well, until the outer layers disappear from view, leaving only the calm surface of the horizon behind. This disappearance is not an event of destruction, but a change in visibility, a quiet shift in what information can escape outward. As light struggles upward, its energy decreases, its color reddens, its frequency drops, until finally it becomes undetectable, lost to the infinite redshift at the horizon. To a distant observer, the star seems to freeze, lingering at the edge, its final moments stretched across an eternity of time, never quite crossing, never fully gone. But from the star's own perspective, the collapse continues normally, passing through the horizon in finite time, falling inward toward the singularity without interruption, without hesitation, without noticing anything unusual. This dual perspective, outside and inside, is one of the quiet wonders of black hole physics, a reminder that time and space are not universal stages, but flexible structures shaped by mass, motion, and geometry. Outside observers watch collapse slow, dim, fade until the horizon remains as a silent marker, while the interior collapse proceeds to its next stage, as if the horizon were simply a mathematical crossing. This is why the horizon is not a portal, not an opening into another region of space, but a boundary defined by what is no longer possible, a surface where outward motion ends and where all future-directed paths slope inward. Imagine standing just inside and trying to fire a beam of light outward. You would see the beam curve, tilt, fall inward, never gaining distance, because the geometry has removed the outward direction. From this point forward, every moment carries you deeper toward the singularity, the mysterious region at the center, where densities exceed comprehension, and where the equations of relativity, so powerful and reliable elsewhere, reach limits they cannot cross. But before we explore that hidden region, it is important to complete the portrait of the horizon itself, to feel its calm symmetry, its lack of physical substance, its total dependence on geometry. The horizon is defined by radius, mass, and nothing else. It does not depend on the star's composition, its history, its temperature, its internal structure, or the chaos of its collapse. All of that complexity disappears, smoothed away by the horizon's simplicity, replaced by a single parameter, mass, and if the star spins, spin, and if the star carries charge, charge. This simplicity is often summarized in the idea that black holes have no hair. But the deeper truth is that the horizon naturally erases details, gently, perfectly, leaving behind a structure determined only by the parameters spacetime cares about. Even now, before the singularity is reached, this erasure is already in progress. The horizon establishes what information can leave and what cannot, and almost all details of the collapsing star remain inside, never to reappear in their original form. Meanwhile, the horizon persists, a surface of pure geometry, a boundary in the structure of space-time. The outer universe continues unchanged. Stars shine, galaxies rotate, neutrinos stream across cosmic distances, gravitational waves propagate at light speed. But at the heart of this collapse, a black hole has formed, defined by the horizon surrounding it, and now the inward journey continues, carrying you deeper into the region where the event horizon no longer marks the limit, but the beginning of the most extreme geometry known to physics, a geometry that will lead, quietly, inevitably, toward the singularity, the place where the equations soften, blur, and finally fade into mystery. The event horizon now rests behind us, a smooth boundary marking the calm surface of a newborn black hole, and inside that quiet threshold, the collapse continues deeper and deeper, toward a region where our equations, so precise, so elegant, begin to whisper, and then fall silent, a singularity, a place predicted not through imagination, but through mathematics, arising naturally from the curvature that grows without limit, as matter descends inward under gravity's complete authority. To understand this idea gently, you can imagine the interior of the horizon as a landscape where every direction slopes downward, a slope that grows steeper with every moment, until finally, no calculation can tell you what lies at the end, because the slope becomes infinitely deep, infinitely sharp, a point where classical geometry cannot continue. General relativity predicts this outcome with remarkable clarity. It describes a region where space-time curvature becomes unbounded, where density increases without limit, where the gravitational field becomes so intense, so compressed, that the usual rules of distance, time, and causality begin to lose meaning. But even here, in this extreme, the collapse is not chaotic, not violent, not turbulent. It is smooth, predictable, guided by equations that only fail at the very end. At the singularity itself, inside the horizon, the radial direction behaves like time. Every moment carries matter closer to the center, not because of momentum, not because of force, but because the geometry requires it, defines it, shapes it into the only possible future. Time and space begin to interchange roles, not metaphorically, but mathematically. The inward direction becomes as compulsory as the next second, and the next second becomes a step deeper toward the singularity. This is one of the most profound consequences of the horizon, that once crossed, the dynamics of space-time rearrange themselves so completely that the collapse becomes inevitable as time flowing forward. To a distant observer, all of this is invisible, hidden behind the event horizon, shielded from the external universe, not by material walls, but by geometry's refusal to let information escape. This is why the singularity is said to be hidden, why it obeys the cosmic censorship conjecture, why the universe ensures that such extreme regions cannot affect the outside world directly, except through the mass, spin, and gravitational imprint they leave behind. Inside the horizon, the collapse continues with perfect smoothness, matter falling deeper into curvature, paths narrowing, the inward direction becoming a funnel whose depth only increases, never stabilizing, never flattening. Classical physics claims that at the singularity, density becomes infinite, curvature becomes infinite, time ends, space collapses. But these infinities are signs, not of reality, but of the breakdown of our equations. A singularity is not a place that exists in the ordinary sense. It is the moment where the mathematics we use to describe the universe stop working, where they predict values that no physical system can contain, and where our understanding must be extended, reinvented, or replaced. Yet even though the singularity represents the limits of our knowledge, the path leading toward it remains calm, smooth, a continuation of the collapse already underway. Matter moves through extreme densities, neutrons pressed beyond their limits, quarks, gluons, and perhaps more fundamental components, forced into states that current physics cannot describe. But nothing resists anymore. Nothing holds back. Nothing pushes outward. The collapse is guided only by curvature, only by the structure space-time has chosen, only by the geometry shaped by the total mass inside the horizon. The singularity sits at the center of this inward flow, not as a physical point, but as the end point of every timeline inside the horizon, the place where all futures converge, the place where all possible paths end. Every object, every particle, every field, every ripple in space-time is carried inexorably toward this region, because the geometry allows nothing else. In this way, the singularity acts like a boundary in time, a moment all infalling matter must reach, because the inward direction has become the future itself. It is difficult to imagine, because our intuition is shaped by flat, ordinary space, where directions stay consistent and time has no spatial meaning. But inside a black hole, the rules change. The coordinates that once described space begin to behave like time, and the equations of general relativity reveal this transformation with absolute clarity. Even as they fail to describe what happens at the end, curvature increases without limit, distances shrink. Time intervals shorten, and matter collapses into a region smaller than anything our theories can express. Quantum gravity, a theory that does not yet exist in complete form, is expected to replace the singularity with something else, something finite. Perhaps a state of extremely compressed quantum fields, perhaps a loop of discretized spacetime, perhaps a region where geometry becomes probabilistic, or where entirely new dimensions of behavior unfold. But until that theory arrives, the singularity remains a placeholder, a question mark, the quiet reminder that nature may be stranger than anything we have yet imagined, and that the universe at its most extreme is still waiting to be understood. Why the singularity is hidden, why the event horizon protects the outside universe from its effects, why general relativity insists on this boundary, all of these ideas converge into the concept of cosmic censorship. That nature conceals the failure of classical physics behind horizons, ensuring that no observer outside the black hole is exposed to undefined physics, ensuring that predictability remains intact, ensuring that the universe maintains order even in the presence of its most extreme objects. This idea, deeply mathematical, yet profoundly reassuring, tells us that the singularity, whatever it truly is, will never be seen from outside, never be exposed, never break the coherence of physical law across the universe. Inside, the collapse continues, reaching curvatures so extreme that gravitational tidal forces become unimaginably large, stretching, compressing, reshaping matter into forms that classical physics cannot describe. Yet even these tidal forces grow gradually, steadily, not in sudden bursts, because the geometry remains smooth, the collapse guided by equations that work perfectly until their final moment. There is a strange serenity in how general relativity describes this descent, as if the universe is gently guiding matter into silence, into a region where the language of physics becomes incomplete, into a place where our tools falter, and new understanding must be forged. The singularity is not violence, it is not chaos, it is a mathematical boundary, the quiet point at which our theories ask for help, ask for revision, ask for a deeper framework. And so, this part of the journey settles into stillness, the inward fall continuing, the curvature growing, the equations softening into uncertainty. All the ideas of this section now rest in place: the meaning of the singularity, the unbounded curvature, the breakdown of classical mathematics, the hiding of this region behind the horizon, the promise of quantum gravity yet to come. And with these ideas now drifting softly in the mind, the journey continues toward the next stage. The stage where the black hole settles, stabilizes, and becomes one of the simplest, quietest objects in the universe. Deep inside the horizon, far beyond the reach of outward motion, the collapse continues with a kind of serene inevitability, a calm descent through geometries more extreme than anything else in the universe, guided only by gravity's perfect, unbroken logic. The singularity, though often described as a point, is not a place in space, but a place in time, an unavoidable moment in the interior future of the collapsing star, a destination written into the curvature itself, waiting at the end of every possible path. To understand this gently, you can imagine spacetime as a fabric whose weave grows tighter, denser, more curved as you move inward, until at last the threads converge into a region that no longer resembles the smooth geometry from which you began. Curvature increases without bound. The lines that define distance and direction twist inward, the equations describing them rise toward infinity, and the collapse moves toward a place where our mathematical description, so precise elsewhere, cannot proceed. A singularity is not chaos, not violence, not a violent tearing of space, but a point where the rules we use to measure, describe, and predict are no longer sufficient. It is the boundary of knowledge, not the boundary of nature. Even now, as matter falls inward, the geometry guiding it remains smooth, the collapse obeying equations that work flawlessly. Until the very last step, general relativity describes every moment of the fall, every narrowing of space, every change in curvature, every shift in the shape of time, until it reaches a point where its predictions become infinite. And infinity, in physics, is a sign that the theory itself needs something more. This is where quantum gravity enters the conversation, not as a complete theory, because one does not yet exist, but as a promise, a whisper, that space-time may have structure at scales far smaller than atoms, far smaller than nuclei, perhaps even far smaller than quarks. Classical relativity treats space-time as smooth, continuous, infinitely divisible, but quantum physics suggests that nature may not allow such infinite precision, that at extremely small scales, space may come in quanta, tiny indivisible units that prevent curvature from becoming truly infinite. In such a picture, a singularity would not be a point of infinite density, but a region where quantum geometry resists further collapse, a region where spacetime cannot be compressed beyond its smallest unit, where new physics must come into play. Some theories imagine the singularity as a dense, finite core of quantum states, a collapsed region where geometry folds back on itself, not into infinity, but into a stable configuration governed by quantum rules. Others propose looping structures, tiny, vibrating networks of spacetime, where curvature is spread across a finite volume, preventing singularities from forming. Still others imagine that collapsing matter may tunnel into another region of spacetime, a region disconnected from our own, creating new branches of geometry, new universes, new expansions. These ideas remain speculative, uncertain, suggestive, but all share a common belief that the infinities predicted by classical relativity are not literal, but signs of a theory reaching its limits. Yet despite these possibilities, and despite the unknown nature of the singularity itself, one fact remains absolutely certain. It is hidden. Hidden behind the event horizon, shielded from the universe, unreachable by observation, inaccessible to light, and unreachable by information of any kind. This hiding is one of the universe's most remarkable behaviors, a form of cosmic modesty, ensuring that the breakdown of classical physics never affects the outside world, never spreads unpredictability across spacetime, never disrupts the coherence of the universe beyond the horizon. This concept is called cosmic censorship, the idea that singularities are always concealed, always wrapped behind horizons, ensuring that the laws of physics remain predictable everywhere else. Whether cosmic censorship is absolutely true, nobody knows, but so far, every singularity produced by gravitational collapse seems to obey it, resting quietly behind a horizon that prevents its extreme curvature from shaping events beyond. This separation is essential, because a naked singularity, one exposed without a horizon, would make physics unpredictable, violating the stability of cause and effect, allowing outcomes to be influenced by undefined geometry. But the universe, at least in the physics we currently understand, does not allow this. Instead, singularities remain hidden, silent, sealed within the geometry of black holes. This hidden nature gives rise to something deeply comforting, that even in the universe's most extreme environments, order remains, causality remains, predictability remains. The horizon separates what can be known from what cannot, and this boundary ensures that the outside universe remains untouched by the breakdown of classical equations. Inside, the collapse continues, smoothly, inevitably, the inward path becoming narrower, shorter, until the timelines of falling matter converge. But even in these final moments, nothing dramatic announces the singularity's presence, because the singularity is not a point one arrives at. It is a moment, a time-like boundary in the future of everything inside the horizon, a moment where the collapse ends, where all timelines terminate, because space-time itself ends there. For the falling matter, the singularity is simply the end of its future, a point it reaches in finite time, though outward observers will never see this moment, never detect it, never witness the collapse completing, because from outside, the horizon hides everything, and the interior remains a self-contained world, a separate region of space-time, with its own future, its own structure, its own fate. This is why the singularity is more than a mathematical curiosity. It is a reminder of the limits of knowledge, a horizon not just in space, but in understanding. We can describe the path leading toward it, predict the behavior of matter falling inward, calculate the curvature, the compression, the shifts in geometry, but at the singularity itself, description ends. And in this gentle retelling, the singularity becomes not a place of fear, but a place of mystery, the quietest room in the universe, sealed behind a horizon, holding secrets no observer can reach, awaiting a future theory that will finally unravel what lies within. With all these ideas now resting softly in your awareness, the nature of the singularity has been explored, its unbounded curvature, its hidden location, its meaning in relativity, its possible resolution in quantum gravity, its role as the endpoint of collapse. And so, with the final concepts of this section drifting into stillness, the journey moves onward, toward the next stage, the moment when the collapse has finished, the singularity has formed, and the black hole that remains settles into one of the simplest, most stable objects in the universe. The inward fall has completed its journey. The singularity rests at the center, hidden behind the event horizon, and now the collapse gives way to stillness, to the quiet presence of the black hole that remains. The star, once luminous, once held in balance between fusion pushing outward and gravity pulling inward, has transformed into one of the simplest objects in the universe, a structure defined not by the complexities of atoms or plasma, but by only three properties: mass, spin, and charge. Everything else, every detail of the star's history, every turbulent wave inside its core, every fragment of carbon, oxygen, iron, every convection cell, every magnetic knot, every flicker of nuclear burning, has been erased, smoothed away, leaving behind a geometry that remembers almost nothing of the star that formed it. This is the meaning of the no-hair theorem, the idea that black holes have no additional features, no irregularities, no distinguishing characteristics beyond these three quantities. Mass determines the size of the horizon, spin twists spacetime around the hole, and charge slightly modifies the geometry. Though astrophysical black holes are believed to carry almost none, everything else is gone, absorbed into the calm geometry that surrounds the horizon, and the universe accepts this simplicity, this perfect reduction, as the final outcome of gravitational collapse. This is one of the quiet beauties of black holes, that from the complexity of a star with its layers, its fusion cycles, its magnetic storms, its turbulent plasma, gravity produces a structure that is smooth, stable, and elegantly described by very few parameters. The outside geometry adjusts itself accordingly, forming the spacetime structure known as the Schwarzschild geometry if the hole does not spin, or the Kerr geometry if it does, each a stable, steady solution to Einstein's equations, each describing how space curves smoothly around the horizon. In the spinning case, something even more subtle emerges, a dragging of space itself, as if spacetime is gently pulled around the black hole's axis of rotation, creating a region where nothing can remain still, where everything, even light, must rotate with the hole. This is known as frame dragging, or the lens-thirring effect, and it reveals that spacetime is not passive, not static but responsive, alive with the curvature generated by mass and spin. Around a spinning black hole, the geometry forms an ergosphere, a region where the twisting of space is so strong that all objects must rotate in the same direction as the black hole, a mandatory swirl, a gentle but unavoidable drift of spacetime itself. Yet even this extraordinary behavior is simple, structured, predictable, guided by equations that produce stable solutions millions, billions of years into the future. The black hole does not flicker or tremble, does not wobble or breathe. It simply exists, its horizon steady, its curvature fixed by its mass and spin, its presence shaping the space around it with perfect consistency. But although the horizon appears calm, its formation often leaves behind faint ripples, gravitational waves created during the final moments of collapse, waves that radiate outward, carrying energy away, allowing the black hole to settle into equilibrium. These ripples cause the black hole to ring, not in sound, but in the oscillations of spacetime itself, vibrations that gradually fade, like the dying chime of a struck bell, a phenomenon known as quasi-normal ringing. The frequencies of this ringing depend only on mass and spin, providing a signature as unique and unmistakable as the tone of a musical instrument, a cosmic fingerprint left by the newborn black hole as it relaxes into perfect stability. Once the ringing fades, the geometry becomes still, smooth, unchanging, the horizon settling into a shape determined with absolute precision by the mass it contains. A black hole, in this quiet final state, is one of the simplest objects in the universe, its complexity stripped away, its history erased, its interior sealed from view, its exterior described by a handful of quantities. And yet, this simplicity does not make it uninteresting, it makes it profound. Because from this smooth, featureless exterior, the black hole imposes its presence across vast regions of space, curving orbits, shaping accretion disks, influencing the motion of stars, sculpting entire galaxies. Supermassive black holes at the centers of galaxies may weigh millions or billions of solar masses, their gravity quietly organizing the dance of stars around them, their presence anchoring the structure of galaxies like calm cosmic hearts. Smaller black holes, The remnants of stars may drift through space, invisible, silent, yet powerful enough to shape the motion of any object that wanders near them. Despite their extreme nature, they are stable, long-lived, and fundamentally simple, the final state of collapse guided by gravity's most elegant mathematics. All the complexity of the star that formed them is gone, yet nothing is lost from the perspective of the laws that govern the outer universe. The black hole's mass reflects the total energy that fell inward. Its spin reflects the angular momentum that survived the collapse. Its charge, if any existed, is preserved. And beyond these, all other details dissolve, buried behind the horizon, inaccessible, unrecoverable, as if gravity prefers simplicity at its deepest extremes. In this way, a black hole becomes a bridge between complexity and reduction, between the turmoil of stellar interiors and the calm, geometric elegance of spacetime shaped by pure mass. It is here, in this balance of simplicity and gravity, that a black hole finds its quiet existence, no longer collapsing, no longer changing, simply resting as a curved region of spacetime, defined, stable, complete. And now, with the black hole settled, with its geometry calm and its ringing faded, the journey turns outward, toward the echoes left behind, the subtle signatures the universe uses to reveal that a star has died and a black hole has been born. The black hole now rests in its final shape, a smooth horizon enclosing the collapsed heart of a star, a region where spacetime has simplified itself into one of nature's most elegant forms, and the universe responds to this new presence with calm, predictable order. Mass, spin, and charge, the trinity of properties that fully describe the black hole, continue to define everything about it, shaping how it curves space, how it influences time, and how it interacts with its surroundings. The no-hair theorem whispers its quiet truth through the geometry, reminding us that a black hole forgets the detailed story of its creation, all the chaotic turbulence of the collapsing star, all the intricacies of nuclear fusion, all the patterns of magnetic fields and convective currents, have vanished behind the horizon, leaving only the fundamental quantities that gravity cares about. This erasure is not violent, not abrupt. It is the natural consequence of the horizon's presence, a surface that absorbs information not by shredding it, but by preventing it from interacting with the outside world, its details sealed away, its influence reduced to the simplest possible form. Outside the horizon, the space-time geometry is stable, analytic, a perfect solution to Einstein's equations, smooth at every point, unchanging unless new matter falls inward. The curvature around the black hole tells the universe exactly what mass lies within, how fast it spins, how it drags space-time around with it, and nothing more. A black hole's spin, especially when rapid, creates a special region just outside the horizon, where space-time is wound into a gentle twist, a swirl of geometry known as frame dragging. In this region, every particle, every photon, every direction of space is pulled into rotation around the black hole. Even if the object itself has no desire to move, it is not a force, not a push, but a transformation of the coordinates themselves. Space-time rotating as a single fabric, carrying everything along with it. This dragging of space becomes strongest near the horizon, shaping orbits, guiding trajectories, and creating the ergosphere, a region where nothing can remain at rest relative to the distant universe, because the twisting of space is too strong. Inside the ergosphere, particles can lose energy, radiate, spin down, in processes that extract rotational energy from the black hole, feeding the jets that sometimes emerge from the accretion disks around supermassive black holes, and powering some of the most luminous objects in the cosmos. Yet even with this complexity, the underlying geometry remains simple, determined entirely by mass and spin, a testament to the quiet order imposed by the no-hair theorem. As the black hole settles after its formation, it rings. This ringing is not sound, but a set of gravitational oscillations, quasi-normal modes that ripple outward as the newly formed horizon adjusts to equilibrium, dampened by the emission of gravitational waves, slowly fading, softening, until the horizon becomes perfectly still once more. These oscillations are the black hole's last active expression of its past, the final echoes of the collapse, and once they fade, the black hole becomes timeless, unchanging, defined by its parameters alone. The ringing frequencies reveal an extraordinary fact that any two black holes with the same mass and spin will ring with identical tones, as if the universe uses gravitational sound to confirm the simplicity of black holes, to announce that all details beyond mass, spin, and charge have been swallowed and lost. This predictability shows why black holes are sometimes called the hydrogen atoms of gravity. Fundamental, simple, beautifully described by a minimal set of variables and serving as clean laboratories for the nature of space-time. And yet, despite their simplicity, black holes influence their surroundings in rich, subtle ways. A black hole can anchor a star's orbit, capture gas, grow by accretion, or remain silent and solitary, traveling through space without emitting light, revealed only by its gravitational tug on the objects around it. In crowded regions of galaxies, black holes may merge, combining their mass, their spin, their horizons into larger and smoother structures. The final black hole still described by the same set of simple parameters, its complexity reduced, its geometry smoothed. After each merger, after each disturbance, it rings again, the quasi-normal modes announcing the new equilibrium, the gravitational waves carrying away the details of the collision, leaving behind another smooth horizon. The stability of black holes is also remarkable. They do not evaporate or decay on human timescales, only through processes so faint and slow that they take incomprehensibly long epochs, many times longer than the age of the universe, to influence astrophysical black holes in any noticeable way. In the meantime, they remain steady, quiet, simple geometries in the fabric of spacetime, their complexity hidden within, their exterior defined only by the calm curvature they impose. Even when black holes interact with surrounding material, accretion disks form in elegant spirals, gas heated by friction and compression, lighting up the region around the horizon, but never revealing what lies inside. Jets, when they occur, are powered not by the black hole itself, but by the magnetic structures in the disk, drawing rotational energy from the hole through processes predicted by general relativity. Yet none of these luminous features break the simplicity of the horizon. None reveal its interior. None disrupt the quiet stability that defines the black hole's nature. In every environment, from isolated black holes drifting through interstellar darkness to supermassive giants at the centers of galaxies, the same principle holds. Black holes settle into perfect stability. Their geometry unchanged, unless fed new mass, their horizons smooth, their properties precise, their influence subtle yet profound. This stability makes black holes the quiet architects of many cosmic structures, shaping the evolution of galaxies, guiding the motion of stars, and sculpting the luminous disks and jets that arise when matter falls inward. They stand as endpoints of stellar evolution, yet also as the seeds around which galaxies form, the anchors of cosmic architecture, and the most extreme laboratories of gravity the universe provides. And now, with the black hole fully formed, fully settled, fully understood in its simplicity, the journey turns once more toward the final signatures left behind, the echoes of collapse that spread outward, revealing how the universe quietly tells the story of a star that has fallen into darkness. Long after the collapse has finished, long after the horizon has settled, long after the black hole has become a quiet, stable, unchanging presence in space-time, the universe continues to carry echoes of what happened, subtle signals, quiet fingerprints, whispers left behind by gravity and light and particles in the final moments before the star disappeared into darkness. Not dramatic, not explosive, but faint traces, slowly fading across space, revealing the birth of the black hole in indirect, gentle, mathematical ways. One of the first of these traces comes from gravitational waves, ripples in space-time itself, created during the last moments of collapse, when the star's structure falls inward, accelerated by gravity, distorted by uneven densities, and sculpted by geometry into patterns that radiate outward. These waves do not disturb space the way sound disturbs air. They stretch and compress distances. Very slightly, very softly, carrying away the energy of the collapse, allowing the nascent black hole to settle into equilibrium. They are faint beyond imagination, ripples so small that the change they create is less than the width of a proton, even after traveling across millions of light years. And yet, in the quiet precision of modern detectors, we can sense them, their patterns revealing the collapse, the ringing of the horizon, the merging of masses, the last moments before the black hole becomes still. These waves contain a language all their own, a language written in frequency, in decay rates, in oscillations of spacetime curvature, each carrying information about the mass, the spin, and the geometry of the black hole left behind. These are the universe's softest messages, sent not through light, but through the fabric of existence itself. Another echo emerges in the form of neutrinos, silent particles that rarely interact with matter, passing through planets, stars, even entire galaxies without slowing, without scattering, without losing energy. During the collapse of a massive star, neutrinos are produced in enormous quantities, released as the core's density rises, as electrons merge with protons, as neutrons form, as the collapse accelerates toward the creation of a black hole. These neutrinos escape the dying star long before the light of the explosion does, their journey unhindered by the thick layers of plasma, their passage barely affected by the matter around them. By the time photons emerge from the expanding supernova shell, neutrinos have already traveled across the universe, delivering the first announcement of a star's death, the first signal that something extraordinary has happened. But when the collapse forms a black hole directly, the neutrino signature may be truncated, cut off abruptly, as the horizon forms and the star disappears into it, leaving an incomplete pulse, a sudden silence, a quiet sign that the collapse went past the threshold of no return. Astronomers watch for this silence, knowing that an interrupted neutrino burst is one of the gentlest yet clearest indicators that a black hole has just been born. Another trace of collapse appears in the supernova shell, the expanding debris that remains when only part of the star falls inward, a cloud of glowing gas spreading outward, cooling, stretching across space. Even if the core has collapsed into a black hole, the outer layers may have been blown outward by shock waves that formed before the horizon appeared, creating a nebula, a shell, an expanding sphere of elements forged during the star's final contractions. Iron, oxygen, silicon, carbon, elements formed during the star's lifetime and during its last moments of intense compression, now drifting outward, slowly, calmly, to become part of cosmic clouds, future stars, future planets. The black hole hides the ending, but the nebula reveals the beginning, the formation of new structures from the remnants of the old. This outward expansion is not chaotic, it is a quiet unfurling, a slow diffusion of heavy elements, a gentle illumination by residual heat and shock energy, gradually fading as the shell expands into space. And although the black hole itself is invisible, the behavior of the supernova shell tells astronomers whether a neutron star was left behind, or whether the collapse continued into a black hole. A neutron star creates a pulsar wind, jets, magnetized structures, but a black hole leaves the shell quieter, smoother, more uniform, its center dark, its evolution governed only by hydrodynamics, not by the presence of a spinning remnant. This contrast becomes one of the universe's clues, a soft way of revealing what happened within. Other signs of a black hole's birth emerge indirectly, not from the collapse itself, but from how the newborn black hole interacts with its environment. A black hole may attract gas from nearby regions, forming an accretion disk, a thin, spiraling structure where matter heats as it falls inward, releasing energy, creating faint or sometimes brilliant radiation, depending on the environment. The disk becomes a visible companion to an invisible object, a glowing halo tracing the path of material falling toward the horizon. In some cases, jets emerge, thin beams of highly accelerated particles launched along magnetic field lines, powered by the rotation of the black hole, pulling energy from the ergosphere, feeding it into collimated streams that can extend light years across space. These jets are not signs of violence, but signs of geometry. Signs that the curvature around a spinning black hole can give structure to magnetic fields, guide particles, and focus them into narrow beams. Even though the black hole itself emits no light, the environment around it glows, swirls, jets, and reveals the presence of the horizon. And farther across the cosmos, the gravitational influence of the black hole continues as the final echo. Stars orbit differently, gas clouds shift their paths, binary systems wobble, galactic centers stabilize around the quiet mass at their heart. Each motion, each orbit, each deviation in velocity becomes a trace of the black hole's presence, another echo of its birth, another way the universe records the collapse without ever looking directly inside. These signatures, gravitational waves, neutrinos, expanding shells, accretion disks, jets, and orbital motions are the universe's soft language, a language of ripples, particles, light, and dynamics quietly revealing that a star has ended and a black hole has begun. And with these echoes drifting into calm understanding, the journey prepares to enter its final stage, a gentle reflection on all that collapse creates and all the quiet wonder that remains. Even when the collapse has ended and the black hole has settled into silence, there remains a kind of cosmic afterglow, not in the form of light, but in the way space and matter quietly adjust to the presence of a new gravitational anchor. One of the gentle signatures left behind is the motion of stars that orbit near the black hole, their paths curving more sharply, their speeds increasing as they move through the steepened geometry. This motion becomes a soft mathematical imprint, a clue that something massive, compact, and invisible has taken its place at the heart of the system. If the black hole forms in a binary star system, the surviving companion may orbit differently, its period shortening, its trajectory becoming more elliptical, its motion subtly altered by the sudden collapse of its partner. Sometimes the companion transfers matter to the black hole, creating an accretion disk again, not from the initial collapse, but from the slow, steady pull of gravity continuing its work over time. The disk glows faintly, more quietly than the violent outbursts of larger systems, but still clear enough to reveal that something dense and compact lies at the center. These small, steady signs are among the most reliable echoes of a black hole's formation. But there are even softer traces, hidden in the interstellar medium itself. When a black hole is born from a collapsing star, its neighborhood changes. Gas clouds shift their density patterns. Interstellar dust flows along new gravitational gradients, and the geometry of space subtly reorganizes to accommodate the new curvature. These changes are not violent. They unfold slowly, over thousands of years, like the settling of sand after a distant tremor. The region around the black hole becomes a quiet gravitational well, a place where particles drift, where dust collects, where faint radiation may be trapped and re-emitted in soft, dim patterns. Even these slow rearrangements contain information, evidence that a massive object has emerged from the collapse. Another echo comes from the absence of certain signals. In some collapses, the star's outer layers are not expelled at all. They fall inward entirely, leaving behind no bright supernova, no expanding shell, no blast wave. This failed supernova, this quiet collapse, becomes an echo of its own, a story told by what does not appear, by the missing light, by the sudden disappearance of a star that once shone steadily in the sky. Astronomers watch for these vanishings, stars that dim gradually, then rapidly, then fall into permanent darkness, their light curves flattening as though a cosmic switch has been quietly turned off. Such disappearances may be among the most subtle signs that a black hole has formed, a silent collapse, a transformation hidden from view, except for the faintest changes in brightness. And as these signatures accumulate, ripples, neutrinos, shifting orbits, expanding shells, vanishing stars, quiet accretion, all weave together into a calm, coherent picture of how the universe reveals a black hole's birth. Nothing in these echoes is dramatic, nothing loud, nothing sharp. The universe speaks softly when a black hole forms. It speaks in mathematical hints, in delicate ripples of spacetime, in silent particles racing outward, in the slow drift of matter around an unseen center. It speaks in faint patterns of light, in the absence of a star that once shone, in cooling debris expanding gently into space. And all of these whispers carry the same message, a message encoded in physics, in geometry, in energy and motion. A star has collapsed, its core has crossed a threshold, a new gravitational object has been born, and the universe, in its quiet, precise, measured way, records the event not in sound or spectacle, but in patterns. Patterns that unfold slowly across time, patterns that drift through space, patterns that scientists decode as though reading the faintest writing in the margins of the cosmos. These echoes do more than reveal the birth of a black hole. They remind us that the universe rarely reveals anything directly, that its most extraordinary events are often hidden behind horizons, behind distance, behind silence. What remains visible are the traces, the ripples, the decays, the motions, the gentle rearrangements that follow a great transformation. And as each echo is studied, each ripple measured, each neutrino counted, each fading supernova traced, our understanding of collapse deepens, our picture of black hole birth becomes clearer, and the quiet architecture of the cosmos reveals itself, one subtle clue at a time. All of these calm signatures lead naturally, softly, to the final reflection, the epilogue, where the journey through collapse settles into rest, and the listener drifts into the quiet wonder that lingers around every black hole ever born. In the quiet that follows the long path of collapse, after the ripples have faded, after the neutrinos have passed through worlds without slowing, after the last fragments of a supernova shell have drifted outward into the dark, there remains a stillness, a calm in which the universe seems to pause, as though acknowledging that something profound has taken place. A star has ended its journey of light, and yet, in another sense, it has not ended at all. It has transformed. It has folded itself inward, gathered the weight of its own history, its fusion, its pressures, its internal storms, its radiance, and carried all of that into a new form, a form defined not by the light it emits, but by the shape it carves into spacetime. The birth of a black hole is not a story of destruction, though it feels tempting to tell it that way. It is a story of rearrangement, of gravity completing a task it began the moment the star ignited. For as long as the star lived, it stood in balance, pressure pushing outward, gravity pulling inward, each holding the other in quiet tension. But gravity never stopped, never weakened, never grew tired. It waited, and when the outward pressure finally faded, gravity finished its work, gently, inevitably, folding matter inward, tightening geometry, closing off outward paths. This transformation is not violent in the deep language of physics. It is a transition from one stable configuration to another, and the object that remains, this black hole, is among the simplest things in nature, defined by only a few properties: mass, spin, charge, nothing more. All the details of the star, its layers, its composition, its turbulences, its memories, are erased from the outside world, folded away behind a horizon that no signal can cross. What remains is pure geometry, a curve in space-time so deep, so complete, that light itself cannot climb out. Yet even in that simplicity there is wonder. For black holes are also places where our equations stumble, where general relativity whispers that its own story is unfinished, that quantum gravity must someday speak to complete the picture. The singularity is not a point waiting to be understood. It is a reminder that our current tools are not yet enough, that the universe contains regions where our knowledge dissolves into mystery. And there is a quiet beauty in that mystery, a sense that beyond the horizon lies not chaos but the edge of understanding, the place where new physics will be born when we learn to listen more deeply. As you rest here, at the end of this journey through collapse, you can feel the softness of that mystery, the way it invites curiosity without demanding answers, the way it opens a peaceful space for imagination. The universe is filled with transformations like this. Stars forming, burning, collapsing, becoming new objects, resting in silence, and shaping the galaxies around them. Nothing is ever truly lost, only changed, reshaped, carried forward in another form. Even a black hole, which seems to erase everything, actually preserves the mass, the gravitational influence, the story written into the curvature around it. In that way, the star continues, not as light, but as structure, as a quiet sculptor of orbits and motion, and the deep architecture of the cosmos. And as you drift towards sleep, you might let that idea settle gently within you. That collapse is not an ending, that gravity is not a force of destruction, but of shaping, of gathering, of guiding. That, even in the darkest corners of space-time, there is order and simplicity and calm, and that the universe, from the smallest particle to the largest black hole, moves not in urgency but in quiet, steady, mathematical grace. Let that thought carry you now softly into rest, as the echoes of collapse fade, as the curvature relaxes, as the universe grows still. And in that stillness, know that you are drifting through a cosmos where even the greatest transformations unfold gently, patiently, in the soft rhythm of gravity and time,